On time for lunch. I want to finish what I was discussing in terms of Monte Carlo sampling, and we'll get ourselves started on the tutorial, and then in the second more informal tutorial slot in the afternoon, we'll have plenty of time, I think, to finish this tutorial for today. So what we're discussing now is how we efficiently choose samples distributed according to this probability distribution, which means how do we choose these updates in our Markov chain. How to choose, say, x k plus 1 from x of k in Markov chain Monte Carlo, such that the data set D is distributed correctly according to P of x, which is the distribution of interest. So let me change notation a little bit. Let me call x k plus 1 with an index nu, and x of k with an index mu, and k plus 1 are such that they lie adjacent to each other somewhere in this Markov chain. What we need to define is a probability distribution, okay, that we call the transition probability, that tells us how to transition from x of k to x of k plus 1, or from mu to nu. Transition probability T, I'll call it mu arrow nu. So that transition probability should in principle be able to take any state in the Markov chain and be able to tell you, the probability at, the distribution at which you should be choosing the next state. So fundamentally, Markov chain Monte Carlo has this stochasticity in its sampling. This is not a deterministic procedure. You can imagine other methods of producing samples that is deterministic, but so fundamentally we're looking at a probability, or we're defining a probability, which makes this, again, stochastic or random. So this probability has to be greater than or equal to 0. It should be normalized, such that starting from any point in the Markov chain, the probability of exiting that configuration to another one sums to unity, and so on. So in order for our data set to be distributed correctly, the procedure by which we update according to this transition probability can be derived according to two conditions. And these conditions are designed so that the active importance sampling, again, gives us a data set that's distributed correctly. So you might have heard of these before. The first condition is what's called detailed balance. And the second is ergodicity. I'm going to talk, bad choice of words. I'm going to talk in detail, about detail balance. Let me just mention ergodicity briefly. It'll come up again in these lectures. Ergodicity is basically the concept that every single mu must be connected somehow by our updating procedure to every single nu. And again, the procedure we're defining is this arrow here. So we must, in our Markov chain, there must be a path, there must be a way of producing a chain that connects every single configuration somehow to every other configuration. So there's no isolated points of configuration space. Because now that we're not sampling according to a uniform random distribution, because we're doing this procedure where x2 is based on x1, x3 is based on x2, we have to ensure that we enforce this, and it's called ergodicity. Every I'll leave it purposely vague. What does it mean to connect? I mean, you can imagine that you have very long Markov chains that connect different configurations and so on. I think generally the idea is that, mu must connect every nu, say in sub-exponential time or something like that. So I'm not going to say anything else about ergodicity. It's difficult to prove, but it's a necessary condition for sampling. But let's talk about detail balance. So detail balance is the idea that the rates into and out of different configurations are somehow balanced, they're somehow equal. Okay, so question? Blue is not visible? -1 for everyone in the other room. That's hilarious. I hope they can see it. Okay, so that's ergodicity. Every mu must connect every nu. Detail balance. So detail balance is a condition on how we transition into and out of different configurations. So in the interest of time, I'll say, okay, so I'll just say detail balance we'll sample the correct stationary distribution, the correct distribution that we're aiming for. Say which I'm calling P of X. If when we transition from mu to nu, the transition probability out of that mu times the probability that we've initially landed in that mu is equivalent to sort of the converse, the probability that we've landed in nu and the transition probability out of it. Did I get that right? Yes. So as a ratio, the ratio of transition probabilities has to equal the ratio of probabilities in this way. This is typically how we derive expressions for the transition probabilities, and it depends on this ratio of probabilities that presumably we know. Okay, so I'll keep it in black. For the purposes of this part of the lecture, we know these. Okay, so for example, in the case of the Boltzmann distribution, because it's an exponential, you see how these ratio of transition probabilities depends on the difference in energy of the two configurations. So that's sort of a nice physical example. So T mu to nu. Did I do this right? Nu to mu. Okay, so we know, say, the Boltzmann distribution for this case, right, and for this case. So I want P of nu, so that's e to the minus beta e nu over z, and z over e to the minus beta e mu. So the partition functions, even though they're complex objects, cancel. And we will use this extensively in our tutorial. Hope you can see that. So the difficulty isn't necessarily in deriving, this ratio of transition probabilities. It's really what is the process by which we jump between these different states that satisfies this condition called detailed balance. Okay. So let's answer that question now with one certain solution for this algorithm. So what is the appropriate process? The thing that I was calling the arrow there. Okay, so this, in general, there's no sort of unique solution for this process, which will satisfy detailed balance. And in fact, you can have algorithms that have, pros and cons. You can have algorithms that are very local, that say flip a single spin, but result in configurations that are highly correlated. You can have other processes, defined by this arrow, which flip global clusters and all sorts of loop structures or all sorts of crazy things you can think about, which may be more difficult to implement, but it'll give you more highly independent samples. So, kind of the art and the state of the art in terms of designing your Markov chain Monte Carlo really goes into this procedure of choosing these arrow, choosing that arrow, that process, which satisfies detailed balance. So one design trick, I'll call it, is to split the transition probability up. So let me take T mu to nu, and I'll split it up into what I'm calling a selection probability and an acceptance ratio. So G mu to nu is a selection probability, and A is the acceptance ratio. The selection probability tells you how you target nu. So sitting in mu, which is xk, so it's that image or it's that vector of binary Ising configurations. What's the probability that I target some other configuration? Once I've targeted that other configuration, A is the probability at which I accept it, hence acceptance ratio. Okay, so let's derive the procedure or algorithm for updating configurations. For the specific case of, say, a Boltzmann distribution. And let me think again of the Ising model. Where I have a configuration mu is xk, is some x1, x2, xi, xn for n qubits or n spins. And as a target, let me imagine selecting this site index I at random and then flipping that spin. Okay, so again, this has some configurations of ups and downs or plus and minus ones or whatever we're calling them. Minus 1, 1. Maybe this is 1 here. Maybe this is minus 1, whatever. So let me imagine designing an update that is a single spin flip. Which takes this and flips it to -1. So you can imagine choosing the site index I at random. And the target state mu is, x of k with xi gone to -xi. So the role of the algorithm, which the process, now becomes whether or not I accept or reject that proposed target, right? So if you propose something crazy, maybe something that violates detailed balance, you want to make sure that your A is 0, okay? But if you propose something that makes a lot of sense, maybe lowers the energy, then you want that A to be essentially 1. And in fact, you want to design algorithms typically, number one, that have as high of an acceptance ratio as possible, but that also give you highly uncorrelated samples, right? So that means if you have a lot of correlation, your data set might have to be bigger to get a good estimator. If you have a small amount of samples that are highly uncorrelated, presumably you can find the minimum size data set to produce your estimator. So this choice of this site, randomly choosing this site, gives us a very simple selection probability. Because I've just chosen at random, this is essentially 1 over n for any mu or nu, or any x to the k. Right? Throw a dice. You'll do this in your tutorial. Select a site at random. That gives you the the selection probability. The goal is now to use detailed balance to derive an equation for the acceptance ratio. Okay. So to make a long story short as possible, the ratio of transition probabilities, which we know, did I write it somewhere? I'll write it out. Okay, looks like that. Keep this in mind. This is P of nu over P of mu. Okay. So, okay, I'll write it here. But now we can insert our expression for G. And that should give us a ratio of acceptance ratios. Sounds weird. There's our G's. They'll cancel. And we know, again, if we're dealing with an Ising model and thermal equilibrium, that this ratio is given by a Boltzmann distribution. So this will just give us expression for the ratio of acceptance ratios. That's e to the nu minus e to the nu. Okay, we're not quite done because we need to decide how much of this to split between the numerator and the denominator in principle, right? And to do that, we invoke, a physical principle for our algorithm, which is that we hope that we can accept configurations which lower the energy, right? So in general, the physical principle of, minimum action I guess, dictates that you want to minimize a free energy in principle, right? What we have access to here is an internal energy, this E. So if we minimize the internal energy, then this algorithm should also give us enough power that we basically minimize a free energy naturally. To say allow this, you can make a choice. Choose that if the configuration E new is what? Less than, let's see if I can screw this up. E new, then the acceptance ratio of nu to mu is always accepted.
Shouldn't it be G nu to mu, A nu? Is it split?
I don't know. Somebody check it for me. It's okay? I think it's okay. I think it's okay. It's nu to mu, mu to nu here, right? I've just decomposed it, and it's this, the ratio's opposite there. Yeah. Okay? So now, if I've lowered the energy by this process, I'm going to accept that all the time. That's a choice I make. But now that constrains this algorithm, so that in that scenario, you know, where mu is of lower energy than nu, then the acceptance ratio going the other way has this Boltzmann factor in it. What that means is when I raise the energy, okay, there's a probability that I accept and a probability that I reject. And I accept with this probability. So again, the algorithm becomes stochastic. I roll a dice, I compare that dice, which is a dice that is a continuous distribution between 0 and 1. I compare it to this probability. Okay? That's called the Metropolis algorithm. It actually took many years to sort of settle on exactly this form for the Metropolis algorithm. This is the form that we'll use in the tutorial today. Okay? I can give you a sort of more precise expression for the Metropolis algorithm that doesn't necessarily depend on the Boltzmann distribution. So let me call that the generalized Metropolis algorithm. That's A, let me get these indices right. Mu to nu is the minimum of, oops. So it's the minimum of this ratio P of nu, transition from nu to mu, and the sort of converse in the denominator. Okay, so here I hope I've motivated the Metropolis algorithm in this specific case. This is what I'm calling a generalized version. Okay, and I want to digress momentarily from this strict example of the Ising model that we're going to deal with today. And I want to talk about this generalized version of the Metropolis algorithm that we're going to use on Thursday when we discuss generative modeling with restrictive Boltzmann machines. Okay, so another case, so you can imagine this is sort of one special case of this formula here. It's one way to design an algorithm that produces a data set that's distributed according to this probability distribution. Okay, that's one way of thinking about it.
That generalized version doesn't satisfy necessarily the minimization of energy, maybe?
It does, because this is the case 1 here, right? And then this is the other
Because
case.
what if the probability that you want to sample has a mean with a specific energy different than 0, then maybe you don't want to minimize the energy, but to get to that particular energy, right?
So you can have a minimum in energy that's not 0, and this will still work.
I mean, that your probability distribution that you want to sample has a mean.
A mean. Oh, sorry.
Yeah, which is not with energy equal to 0. Then minimization of energy is not like what you want.
Okay, sure. Yeah, right. Yeah, so I think the principle that we chose for case 1 there basically assumes that we have this, minimization of the action or whatever it's called. But there's many other versions. Let me put it that way. Let me talk about another specialized case of this. Which is relevant for the restricted Boltzmann machine on Thursday. And this is called Gibbs sampling. So Gibbs sampling and Metropolis sampling are often considered very different. But this formula here, which I've tried to motivate, is a way of connecting the two. Let me put it that way. So if you see Gibbs sampling, it's nothing to be scared of. All it is a sampling with conditional probabilities. So the idea is you can imagine proposing an update on some subset of the spins conditioned on the state of the others. And in some sense you're already doing that here. You're proposing an update of this spin that's conditioned on everything else, right? Conditioned. So that's kind of the important word. Conditional probabilities you can formalize. So maybe this is a review, maybe not. But a conditional probability, I just write like this with a horizontal bar here. This is the probability of A given B. Ugh, big A. A given B. Okay, the probability of A, this probably makes sense, is the idea that if you trace out all possible configurations of B in the joint distribution, you're only left with a function defined over A. So this is marginalized, or the marginal distribution. And marginalized for us means trace. So I'm just relating, a probability to a conditional probability, or sorry, to a joint probability that's been traced over. So that P of A comma B, that's kind of the probabilities that we're used to dealing with. It's the probabilities over the whole ensemble. It's called the joint probability. And the relationship between the joints and the marginals is given by the so-called product rule. So P B conditioned on A, P of A. That's just an exercise in what's called conditional probability distributions. Okay, so when we have all the Ising spins together, and we have a Boltzmann distribution, that's kind of the joint distribution. What I'm asking you to imagine now is that I pick a subset of those Ising spins, and let me call it A, and let me propose an update on A while holding B fixed, then that means that the G in my algorithm is this conditional probability. It's the probability of a new configuration of A with B fixed. So let me go back to my previous notation, and I'm just going to use the rules of conditional probabilities to define what we call Gibbs sampling using this generalized Metropolis update, or Metropolis algorithm. So it's back to, say, Ising variables, x. So this is my mu equals x of k, say. It's a bunch of variables. I'm going to take x of I and I'm going to treat it specially. I'm going to pull it out and calculate a conditional probability. So the algorithm, the update, very generally now, is to just replace this variable, right, with some other variable drawn from the conditional. Its value is still either plus one or minus one for the Ising model. Right, but what we're going to do is draw that according to the conditional. So what I'm going to call, you're going to hate this, P xi, conditioned on the values of all the other variables in this list with I omitted. Okay, so that's just notation. Okay, so it's like I said, I'm conditioning my probability of choosing plus one or minus one based on the values of everything else. You see how it's very similar to what I've been doing before? I'm just formalizing this in a different way. With these expressions for conditional probabilities. So now my G, right, which is my, the hell did I call it? Update probability, is this conditional. So I'm going from, say, mu to nu. Mu is my original vector here. Nu will be the one with this replaced according to that conditional probability. So I'll just call this P xi, right, which is my new value, x minus I, vector, which is that vector of all of the other values with index I omitted. If this isn't confusing, these are unchanged. So this conditional probability of the new value of spin I is also equal to the conditional probability conditioned on all the new values. So in that step from mu to nu, this arrow, only xi changes. And in fact, you can imagine Metropolis, Monte Carlo, Markov chain Monte Carlo algorithms where instead of a single spin, so that should not be a vector, instead of a single spin, I can imagine having two subsets, right? This could be a vector or a subset of more than one spin. And in fact, we'll see this on Thursday when we talk about the restricted Boltzmann machine. So a curiosity of the conditional probabilities, in this case, is the expression for the acceptance ratios given these things. Okay, so this is, let's see, P, this is the conditional probabilities, this is my G. So let's also note that in that expression we need the marginalized distributions, or sorry, the joint distributions. So let me say P of nu, using this product rule, which I'm just defining like this now. This is the full, do I like that notation? Sure. This is the full vector. Is the conditional. P xi times a joint. So I've just used sort of the product rule here. And I did this wrong because that has to be the marginalized one there. Is that right? Did I do that right? Now to derive this, all I got to do is drop in an expression for P of nu and P of mu using that. And I already know what these are. These are the conditionals. And you can do it yourself and see what you get. But that ratio, P of nu, P of mu, so let me write the first part like this, and then this is my G's. And I've taken advantage of the fact that all the other states that I've labeled by minus I don't change. Now I'm deriving this thing here. Let me just leave it on there. And let me substitute in this expression here. So you'll see looks like this finally killed my marker. Now let's see if I did that right. This in the numerator is the same as this. This in the numerator, this in the numerator is the same as this expression here. So you're left with the ratio of these two terms. But remember, what I've done is I've updated site I, and this is the vector of everything except I, right? So these two things are the same. I can change the label from mu to nu here, or vice versa. So the acceptance ratio in this case will always be equal to 1. And so that's just a nice feature of Gibbs sampling. So this is in Gibbs sampling. So Gibbs sampling is just a different type of Metropolis sampling in some sense, where you've changed the expression for G from something that's completely uniform and random to something that's conditional. Okay? We're not going to use it today, but you're going to use this on Thursday. So this is essentially how Boltzmann machines, which are a type of generative model, are sampled. Any questions on this? I suspect that's something you haven't seen before, even if you've seen Markov chain Monte Carlo. So I want to go back to the original Metropolis algorithm for the Ising model, and what we'll do in the next 10 minutes is just discuss what we're going to do in the tutorial, and then we're going to break out our laptops and start exploring these algorithms, and then we'll finish up with that after lunch.
select only according to whether, no, you simply replace the ith coordinate or the ith set.
You replace the ith value with something that's drawn according to that conditional distribution. That's it.
Set it always over.
Once you do that, you accept it with acceptance ratio 1. Yeah. And again, it's different than the original Metropolis we looked at because you have a uniform distribution where you kind of pick at random, but then the acceptance, you can have an acceptance or a rejection step. So how the rejection works in the Gibbs sampling algorithm is you may have configurations of certain variables that basically never get chosen because the conditional probability is very low. So that's all it is it's kind of changing this conditional probability into a different part of the algorithm. It's mind-boggling. Like your mind's all bottled up. Okay, we're going back to the Ising model. What are we doing with our lives? So, this is the tutorial. Again, 2D Ising. You'll have an energy. Maybe I wrote it with a H, I forget. I'll put a J in there because there's a J in your code. This is all bonds on a lattice. Typically, we set J equals to 1. The lattice, here's a lattice here actually. So let me draw a 4x4 lattice. In 2 dimensions. That sum runs over every bond, which is, that's supposed to be a J, which is the label, say IJ here, or IJ here, say. So for every site, you can convince yourself that there's 2 bonds. There's 2, there's 2, there's 2. I'm also periodic, so here's 1, here's 2. And this site here is this site here. Same with up here. I have 2 bonds per site. All right, this site here is this site here. Does that make sense? That'll be you'll have a data structure for that. We're going to update mu to nu with a Metropolis single spin flip. Algorithm. The first thing you'll do is you'll look at the expression for the energy, which in its sort of full naive form has this sum over all bonds, again, which is 2 to the n. 2 times n bonds. But you'll see with the single spin flip Metropolis update, updating that energy every time is kind of overkill, because if I have 4 sites here in my lattice with 4 bonds, and I flip this site I, you'll see that I only affect the local part of the lattice. So you'll be looking at the change in energy locally for a single spin flip. I'll show you in a minute on the projector. The goal will be to calculate estimators. Expectation values of, say, the energy, magnetization. We'll calculate the specific heat, and we'll also calculate the susceptibility. So we know the specific heat, which is beta squared E squared minus E squared. The susceptibility is beta times, I haven't derived this, but you can do it for fun tonight, is the mean squared fluctuation of the magnetization. And as I'll explain later, we use the absolute value here. Let me get back to that. So we're going to calculate these 4 estimators. And we're going to do it with the goal of seeing a phase transition. So in the 2D Ising model, there's two distinct phases in the thermodynamic limits. So if I draw a phase diagram, that is basically the only free parameter left in the free energy, say, which is the temperature. It looks like this. So here's temperature, or T over J. All I'm going to say is a label, and you're going to explore what these labels mean. And one label is ferromagnetic and one is paramagnetic. The ferromagnetic, or low temperature, so if this is T equals 0 here, low temperature state is basically defined by a low energy, all spins up or all spins down. So if you've taken stat mech or condensed matter, you know that in the thermodynamic limit, which means when the number of qubits n goes to infinity, you spontaneously select one of these two states. But you'll explore how these states are selected in the tutorial. So the magnetization, or maybe the absolute value of the magnetization per spin, should be 1 here. Where the magnetization, I'll just do it like this, is defined as sum over I from 1 to n sigma I. Right? Here, you should have a magnetization in the paramagnetic phase that averages to 0. And the absolute value is because you might get two of these states contributing, so I could also look at the absolute value of the magnetization here. This point is the phase transition. It's a sharp distinction between these two labels, or these two phases. And Tc over J is 2.269. Do I have the exact expression? I think it's in your tutorial worksheet. No, I wrote it down. 2 over log 1 plus root 2. The Onsager temperature, 2.269 in units of J. So what we're going to do is we're going to explore the transition between these two states numerically. And what you'll do is you'll calculate things like the average magnetization per spin as a function of temperature for various discrete temperature points. And you'll see something that turns on at Tc and should saturate at a value of 1. And actually here, you might see some finite size remnant, but basically should saturate in thermodynamic limit to a value of m equals 0. So these estimators, which you're going to calculate from the data set produced by Monte Carlo, are the things which basically tell you, in this case, what the two labels are. So one of the interesting philosophies of machine learning is whether or not we can replace some of these estimators in Monte Carlo with something like supervised learning that you're going to learn about tomorrow, which is just a way of assigning these labels not directly through a physically sort of relevant estimator, but through something like a feed-forward network or some other type of classifier. Okay. So as we go forward from today, I mean, all of this is sort of conventional, if you will, statistical mechanics or condensed matter physics. What we're going to think about is how we kind of replace paradigms of calculation that we've developed over decades with other paradigms that have come more recently out of machine learning. Okay. So let's look at magnetization, energy, susceptibilities. We look at all these conventional estimators now in our Monte Carlo code, and basically sort of hash out this phase diagram before we move on tomorrow. So I'm going to pause here before we start our tutorial and take questions. Questions from you guys and also questions from the other room. I don't know how that's going to work. So let's start with you guys. Any questions?
So you know that the chain is ensured to converge to the right distribution. But eventually, and the question is how do you, if I start doing this averaging, am I not using samples with the wrong distribution at the beginning?
Right, so the question is how do you know that you're converging to the right stationary distribution? I didn't actually derive detailed balance, but that's one of the conditions that you need to satisfy. And it's basically balancing the rate equation into and out of different configurations.
No, wait,
But-
it's not, I understand that because of detailed balance you converge eventually to the
Right.
distribution. The question is, the problem is the eventual part.
The question is eventually, right? So there's two answers to that. One is the fact that you have to be ergodic in, I just vaguely define the concept of ergodicity, which is the concept that every mu has to be connected to every nu. Okay, so you can refine that definition a little bit more. So what does eventually mean? It means that, in, say, the time of the universe, you sample all possible configurations. In reasonable computational time, you sample all possible configurations. In sub-exponential time, perhaps. So there's many different, I think, definitions of eventually, of what you called eventually. And for us, I think it's very practical. The time it takes to explore phase space or configuration space grows with the amount of qubits or the amount of lattice points. So what we'll do is we'll converge these estimators in a reasonable time on your laptop for a small system size. Then we increase the system size, and so on and so on. And basically, at some point, within reasonable resources, you won't be able to converge. And that's a very practical definition of how we do these things. So we tend to do them systematically, starting from small sizes and increasing. And what you're looking for, the goal will be the thermodynamic sort of value of this. The thermodynamic value, when n goes to infinity, might look something like this. Do we get there? That depends. Other questions?
How do you guarantee that the minimization energy is get in the Gibbs sampling? Because you don't use that in the argument to get the acceptance ratio equal to 1.
Well, you use it somehow in this expression for the fact that you have a minimum and another term. But yeah, so it's not directly, so I actually don't know the answer to that. I haven't thought of exactly the motivation for this form of the Gibbs sampling. But I think the fact that you have a ratio of acceptance ratios, for lack of a better word, and you have to choose. You have to make a choice about what the value of the numerator or the denominator is. There we made a choice of the denominator. The fact that if you lower the energy, you have an acceptance ratio of 1. And this also appears in this generalized expression. So I don't think I have a better answer than that off the top of my head. It's also possible, I believe, to have Gibbs sampling that doesn't use exactly this expression. So this is, there's a long history to these types of rejection algorithms. I think they didn't even strictly converge until the 1970s with this famous paper by Hastings. So, even though Metropolis sampling was sort of derived in the 50s, some of these things weren't fully fleshed out until the 70s. So I think there's a lot of different options, but these are the ones, this is the form I think we're going to use in this school.
I have a question. Well, in this case, and this connects to Mauricio's problem, we have a very small system size. It's only 16 sites.
Sure.
So as we increase, for example, the number of sites that we would like to do, would it be, let's say, for instance, a very good technique that instead of using a single spin flip, to say multiple spin flips, for example, a pack of spin flips, so that we can get into an acceptance ratio which actually samples the phase space more efficiently? So that's what
Yeah, absolutely. So the best case scenario is that every adjacent configuration in your Markov chain is completely independent, measured by some autocorrelation function, right? So which autocorrelation is just the correlation between step k and step k plus whatever, j. So in principle, you do want algorithms that are non-local. You can imagine why. Because if you do a single spin flip, you're highly correlated. Yeah, so true. In reality, what you do is you design these algorithms as I would say as non-local as possible, so that you get independent configurations, but you still have a high acceptance rate, maybe on this side. So in particular, when you traverse this transition, it's well known that single spin flips give you an exponential slowdown in the exploration time of configuration space, exponential in the number of sites. So there's a type of algorithms which are called cluster algorithms. You might have heard of Swenson-Wang or Wolf algorithms, which actually reduce the complexity of the sampling from exponential to polynomial. And there's specifically sort of highly designed updates to get around this. So actually, in general, again, the art of the state of the art is really designing algorithms that give you a high acceptance rate or high acceptance ratio, but also give you highly independent samples.